discussing on coding aspects for CFD. So the main objective of computational fluid dynamics course is, one thing is to kind of help you to understand the concepts. The other thing is, when you go on to practical applications, you should be able to develop your own codes if the software doesn't have it already. So for that purpose, you need to also learn coding for this particular course. I mean, you all might be already knowing coding, but using CFD to kind of solve the equations. So that is what we will be trying to see in today's session. Okay. So yeah, so can you guys briefly write on the chat box what were the main things which you learned in week 6 contents? So already a hint I have already given, which is the solution of hyperbolic PDEs. So can you write down on the chat box which were the main equations which were physically relevant which you saw in the week 6 contents? Can you write in the chat box? I mean, what kind of physics were you trying to solve? Yeah, Divyendu has written ut minus aux. Yeah, that is exactly correct. Yeah, wave equation. So it is a wave equation, but which physics are you attempting to solve through that wave equation? Can you write that on the chat box? So, in particular, which wave equation? Positive x direction moving wave. So let me reframe my question. Okay, so in which areas do you apply this wave equation to get which quantities, like, of physical interest? Others can also participate. So Dibyendhu has written that it's a wave equation which we are trying to solve in the week 6 contents. So what is the main physics which we are attempting to solve there? Like, I mean, I am asking just for examples which this wave equation will be able to solve. For example, in the Navier-Stokes equation, we solve for fluid velocities and pressure. So, wave equations, what kind of physics do they solve mainly? So that is what I am asking. Inviscid, yeah, partially correct. That is for fluid. If you kind of assume inviscid nature, but again, what happens is that you get non-linear equations. But whereas here you study only linear wave equations, right? So it's not completely correct. Apart from fluid, can you think of something else also, which was mainly, yeah, Burger's equation, correct? So you try to see how we can model the acoustic propagation, that is the sound propagation, through these wave equations. That is the main application of the wave equation, I would say. Because see, the sound gets generated mainly due to changes in fluid flow only. But again, it's a different physics. I mean, the physical model is different, which this wave equation can solve. Okay. So that's the main thing. So you are solving for acoustics through this wave equation. That is just one particular application. So which was mainly discussed in your week 6 contents also. So that is what I was discussing about. Yeah, the other answers are also correct. Also, I think Dibyendu had mentioned only one particular equation, that is ut minus a into ux, if I see it. So what was the other equation? This was a first order equation, I think. So apart from this, did you guys also see through the other equation? If so, can you write down on the chat box? which was the other equation which you saw apart from this ut plus a into du by dx, that is ux. Okay, utt is equal to a square into uxx. Yeah, so that is a second order wave equation. Okay, so mainly these two equations actually kind of reflect two different physics, I would say. So sometimes the velocity perturbation, which is the acoustic perturbation, is modeled using the first order wave equation. This is just for your knowledge purpose. I mean, this is not there in your syllabus. Whereas this second order equation, this usually is used to model the acoustic pressure. So because I particularly work in the area of acoustics, so I have seen these equations. So these are just the physical applications of these particular governing equations. Okay. Okay, so that was one thing which you kind of studied in this hyperbolic PDs. So starting from the course, so this is week 6, so this is halfway through the course. So first of all, you kind of studied the different discretization schemes, and then using the Taylor table approach, how you can come up with a conversion for partial differential equation into the discrete equation, that is dou square u by dou x square, dou square u by dou t square, how you can write in terms of discrete values at the grid points. So that you had seen in the week 2 and week 3 contents, I think. And then slowly once you got the equation, that is the linear algebraic equation, then you studied various solution schemes, for example the Gauss Seidel, and then the your TDMA tridiagonal matrix algorithm. Okay, so those equations, those solution schemes you saw. And then lately you have been seeing in week 4, week 5 and week 6. Okay, in week 4, week 5 and week 6, uh, basically how you can do the time marching for different equations. So in week 4 you saw elliptic equations, which were mainly the Laplace equation, the which gave the steady state heat conduction results. So that was week 4. In week 5 you saw unsteady state heat conduction, which was mainly parabolic equation. So in that condition, which time stepping scheme will be more stable and all, so that you saw through. And in the week 6, which is the current week, you have seen the hyperbolic equations. Okay, and which are the schemes. Okay, there is a question on the chat box. Let me just see. What is acoustic pressure or sound wave? Is it any different? Yeah, see, always what is measured in acoustics are different quantities. See, for example, if you are measuring the uh, vibration which is coming as an acoustic wave, so that as a sound wave, so that indicates the velocity perturbation. So that can be called as sound wave. Okay, because ultimately, see, for example, if you are measuring through any device, for example using a stethoscope, if velocity if the sound signal is being measured, it is nothing but the velocity fluctuation which is coming on the surface, which is being measured. Okay, or the acceleration, either the velocity or the acceleration, which is being measured. So that is one particular form of sound wave which is being measured. Now the acoustic pressure, you know, it is the pressure which is being measured. So it's just the measurement which is becoming different here. So you have different mathematical models to kind of get the values of acoustic pressure and say the velocity perturbations and all. Okay, so that is the main difference here between the acoustic pressure wave or in general sound wave which you call. Okay, so then if you tell sound wave, it is not very specific. It can also mean pressure, it can also mean the velocity perturbation. Okay, so it's like say Navier-Stokes equation, and so it can mean you are solving for fluid velocity also, you are solving for pressure also. Okay, so but if you say acoustic pressure, then it is specifically only acoustic pressure. Okay, I hope that answers your query. The second question is, in case of wave moving along negative x direction, Solution is e raised to minus this equation. Solution. Okay, we'll come to this later on, because what are you trying to tell that the exact solution will be e raised to I into kx plus at? In this equation, should we put a is equal to minus 1 minus 2? Yeah, so if you have got it, like assuming taking the only the magnitude of a, then whatever a is there, that you have to put it. Okay, so I am asking for the sign of a. So yeah, so if the wave is moving along the negative x direction, if the a value is less than 0, that is, I think you mean to say the speed of sound only, right, by a. So yeah, so that will be negative only. You have to put minus 1 or minus 2, whatever speed of sound is there. So see, because you are analytically deriving it, right? Analytically deriving the exact solution. I mean, so if you are landing up with e raised to I into kx plus at, so then yeah, definitely you have to put whatever value of a is there in that equation. Okay, so I hope that answers your query. So you are trying to tell the speed of sound only, right? I mean, the A value which you are telling, it means the speed of sound only, I hope so. Or the speed of propagation, whatever, I mean, in particular sound. Okay, so these were the things which you saw in this week. After that, you have seen different numerical schemes, okay, which are used to solve the wave equations, starting from forward time central space, then forward time forward space, and you kind of saw that many of these schemes were unconditionally unstable. That is, for any delta t whatever you take, these schemes were becoming unstable only. They were not stable. So for one particular scheme, I think you saw that the scheme was becoming conditionally stable. So can you guys write down on the chat box in which cases the solution was becoming stable? I mean, conditionally stable. So what was the main criteria uh, through which you can get conditionally stable? Okay, FTBS when a is greater than 0, Courant number. Yeah, Courant number, it gives that the conditional stability, because for some Courant numbers only you get stability, but what I was asking is which schemes. Okay, so I think Varuni has written FTBS when a is greater than 0. Yeah, in specific you can write like that, that is forward time backward space, so when a is greater than 0. But what is the general principle? Okay, the scheme, exactly, I agree that it is FTBS when a is greater than 0. When a is less than 0, some other schemes. But what was the main physical understanding for getting a stable scheme? I mean, conditionally stable scheme. Can you guys write down on the chat box? I'll just share my screen to just explain that concept. Okay. Uh, is my screen visible? Can you write down on the chat box? Is my screen visible? Can you write down on the chat box whether my screen is visible or not? Whether my screen is visible or not? Okay, thanks. Okay, so basically, uh, this is your computational stencil. Assume that. Okay, this is say your I minus 1, this is I the grid point, and this is I plus 1th grid point. Okay, and assuming that the wave is propagating in positive x direction. Okay, that is a is greater than 0. Okay, but it can be generalized. Okay, for even a is less than 0. Okay, so you want to calculate the value of the variable at this particular ith grid point. So when the wave is propagating in this positive x direction, say, so you have to always take only the value of variables at the previous time step at or the current time step only in the uh, upstream direction, that is only in I minus 1, I minus 2. Okay, because the wave has already traveled those points before coming to the ith point. Okay, okay, so that is the main logic. So if you are taking I plus 1 while calculating the value of variable at I, the wave has not traveled to that particular point at that time instant. Okay, so that is why if you take this, then the scheme becomes unstable. Okay, I hope you get what I am trying to say here. So that is why you have to take only the grid points which are before this ith grid point if the wave is traveling in positive x direction. Okay, this particular points are called as upstream points because the uh, wave has already traveled through these points. Okay, these points are in general called as upstream points, that is the technical word. Okay, so you have to always take into account only the upstream points while calculating the while formulating the solution scheme. Okay, so that is why FTBS, which is the backward space, will give stable results. Okay, for A is greater than 0, that is when the wave is moving in positive x direction. Now similarly, if the wave was moving in negative x direction, say in this particular direction, then the upstream becomes these points I plus 1 and then the I plus 2. Okay, so that is why you have to consider these points. Okay, I hope this is clear to you. Okay, so yeah, this is one thing which I wanted to discuss. So in this way you have to decide the scheme, okay, based on the value of A. Okay, so apart from this, you have also studied the dissipation errors. Okay, and I think the diffusion errors and the amplitude errors which come in, but these things will be discussed in the next tutorial session which will be held on Sunday. Okay, so mainly I'll be going through till calculation of your amplification factor through which you can determine whether the scheme will become stable or not. Okay, so those things I'll be discussing today along with the how you can write a code. Okay, so these sources of errors and then the different schemes through which you can get a stable solution, that is the your leapfrog scheme and your crank Nicholson scheme, those will be discussed in the next tutorial session. Okay, we will also try to solve some of the sample problems based on these topics. Okay, so yeah, so before starting with questions, okay, I'll just try to share with you some of the uh, main things which you have to go through when you write a code. Okay, because in this computational fluid dynamics subject, as I told earlier also, main thing is you have to learn how to write computer programs to solve the physical problems. Okay, so that is one of the main objective, and due to some unavoidable circumstances, these coding questions cannot be given in your assignment. Okay, so that is why we will try to have every week some coding problems to solve. Okay, so that you kind of get a good feel about this CFD subject also. So today we will try to solve a simple unsteady state heat conduction equation, that is mainly from the week 5 contents. Okay, so you basically have a 2D metallic slab as shown in this figure. Okay, and basically you have fixed temperatures at this west boundary, at this north boundary, at this east boundary. You have fixed temperatures. Okay, but at the south you have an insulated boundary. Okay, here q is equal to 0. Okay, heat flux is 0. That is the insulated boundary condition. Apart from that, all the other boundaries are kept at a constant temperature, and you want to study how the temperature variation occurs in the internal domain. Okay, when these boundary temperatures are given. Okay, so you are trying to model this as a unsteady state. Okay, you can try to solve it as a steady state problem also, uh, but we will try to see how you can decide the time step size and all. Okay, because mostly in physical practically relevant situations, the unsteady state problems are more common. Okay, so that is why you have to look at the solution schemes for this particular type of physics. Okay, so the first thing, and is this MATLAB screen visible to you? Can you write on the chat box if this MATLAB screen is visible to you? Okay, thank you. Okay, so you have decided the problem statement now. Okay, so the first thing you have to do in this is define the length of the domain and then the number of grid points. Okay, so the length of the domain you can write it as something like Lx is equal to 1.0, and currently I am doing this in MATLAB. I will also share a simple C program code also with you uh, in the Google Drive, which I upload this PPT. Okay, you can go through that also. The second thing is you need to determine the number of grid points in the x direction and in the y direction. So for example, I am taking just 20 grid points. Okay, 20 cells. So there are 21 number of grid points. Then the second thing is, after deciding these things, you have to calculate the delta x delta y values, that is the geometric parameters. Okay, so del x, how you can calculate? Lx divided by nx minus 1. Similarly, del y is equal to ly divided by ny minus 1. Okay, so this you have decided now. So what is the other thing which you have to decide in an unsteady state heat conduction, which is the other important parameter? uh, Del x del y is one thing, okay, which you have calculated. Apart from that, you have one more thing. Can you write down on the chat box which is the other important parameter which needs to be calculated before doing the time marching? I mean, can you write on the chat box? Ratio of grid spaces, that is delta y by delta x. Okay, that I'll do. I mean, that is not necessary also, but if it is necessary we can do that. But other parameter, one is the spatial, yeah, time step. So that is the very important parameter which we have to calculate next. Okay, so how do you determine the time step size? So that is mainly determined using your stability condition. So I am using say for example forward time and central space scheme. Okay, so it is conditionally stable. So you know that these schemes FTCS are stable only for the diffusion number less than 0.5. Okay, and for 2D, diffusion number is given by which equation? Alpha into delta t divided by 1 divided by dx square, okay, plus 1 divided by dy square, delta y square. Okay, so that is the way in which you calculate d, and this should be less than 0.5. So in this way you have to select the delta t value. Okay, So what you should give is, first you should specify my d value. So it should be less than 0.5 to get a stable scheme. So let me say zero point 0.1. So my diffusion number is zero point 0.1. So based on this diffusion number, I'll calculate the delta T. Now delta T, you can see from this particular equation, you need to calculate it. Okay, delta T is equal to d, okay, d divided by alpha star 1 upon del x square plus 1 upon del y whole square. Okay, so this is the way in which you calculate the delta T value. Okay, so this is one thing. Okay, so in MATLAB, many of you might be familiar. This is just the main editor screen, and you can just run the code to check whether everything is going correct or not. So usually you have to do this at each and every step which you write. Okay, because you will then come up with errors which you see. Okay, because if you do this at the end, okay, so it will, you will go into a very deep problems, because you will not understand where to debug. Okay, so it is telling that alpha have not defined. Okay, alpha is nothing but the row by KCP. Usually it is 0.01 or 0.001. So as of now I am taking just 0.01. So then you kind of get the variables in this workspace. Okay, so delta T, it is determining it as 0.0125. Okay, so I have now determined say delta T and delta X, delta Y. So I am ready to start the time marching, but before that I have to initialize. Okay, so I have T at n plus 1 and T at n, which I have to store. Okay, I'll just store it as T old, okay, and T new. So I have to initialize it, and be very careful when you are writing with MATLAB. Okay, it kind of stores it in rows and columns. So you have to write zeros of ny comma nx, because columns is nx, that is the x direction. Okay, so that is why this nx will come in the second index. Okay, uh, okay, that is the main thing which you have to keep in mind if you are writing it in MATLAB. Okay, the same thing. Now once you initialize, you can start with the time marching. Okay, so I'll just write while our max error, which is nothing but t new minus t old divided by delta t, which we had discussed in the last week also, till it is greater than say 1 into 10 into e power minus 4, sorry, 10 power minus 4. Just run the calculations. Okay, also I need to initialize the max error also first before starting with the solution, so that it enters this loop particularly. Okay, so once it enters this particular loop, what you have to do, apart from solution, which is the main thing which has to be satisfied, the main thing apart from the time marching which we have to write in our code, can you write down on the chat box? RMS error global, see I am taking local here. Okay, I will define it at the end of the time marching. Okay, so but once I need to get the t old and t new. Okay, after that I'll calculate the error. Okay, but before that, what is the very important thing which needs to be satisfied at each and every time step? Okay, at each and every time step we have to satisfy the values of temperature at some points. What is that called as? Can you write on the chat box? Yes, the BNB was written. Yeah, Dirichlet and boundary condition. Yeah. So at each and every time step, we have to make sure about the boundary conditions. Okay. So first I'll decide the boundary conditions. So for example, at the say west face, I have I is equal to 0. I index, I denotes the X index. Okay, it is usually used in your weekly contents also. So I'll write T new or T old, because we will be using Tn. Okay, using the time marching, so that is why I am taking T old. Okay, T old of, okay, and be very careful. Okay, you have columns, rows and then columns. Okay, so in the second I will come. Okay, but in the first actually J will come, that is your the number of rows, that is the y direction. So y direction index is J. Okay, let me write that also. Y is J and X is I. Okay, that is the index notation. But MATLAB stores it as first rows, then followed by columns. Okay, so that is why first J will come, because rows will come. No? So rows are nothing but the y direction. Okay, so that is why J. So now J, you have to be very careful. It is 1 is to n pi. Okay, the index starts from 1. Okay, in MATLAB, so that is why I have taken from 1. If you are writing a C program, it starts from 0. Okay, 1 to ny. There in C program it will be 0 to ny minus 1. Okay, T old of 1 to ny comma your I, that is 0. Okay, now that is equal to, say I give some 100.0, that is the west boundary condition. So similarly I define it for the east. Okay, I'll just copy paste this. Okay, I is equal to nx, sorry, so this should be 1. Okay, it should not be 0. It next starts from 1. Okay, nx. Okay, so again here let me write it as 200, the east boundary condition. Okay, and then you have north. Let me start from south. Okay, so south, here J will be 0, that is the y index. J is the y index. Okay, so J will be 0. So here T old of, say, J comma, now I will be varying from 1 to nx. So here I have told that at the south boundary it is say insulated boundary condition. So uh, T of 1, sorry, again not 0, T of 1 will be equal to T of 2, that is dt by dx is 0. It is an insulated boundary condition. So that is why you have T of j plus 1. Okay, so this is the boundary condition, the Neumann boundary condition. Okay, then you have at the north again the Dirichlet boundary condition. I'll just copy paste this. Okay, so again J is equal to ny and this will be fixed value. Say I'll take, say 100, again 0.0. Okay, so we have now established the boundary conditions. Now we can do the time marching. Okay, so the time marching, when we do, we require the equation is like dt by dt, that is the temperature time derivative, is equal to alpha into d square t by dx square plus d square t by dy square. Okay, so just let me write that. Let me write u instead of t so that it won't cause any confusion. Alpha star, what you have, u xx plus u yy. Okay, so I need to calculate uxx and uyy. I'll just write it in the for loop. Okay, so that it will be better for understanding purpose. So I'll start with 2 because 1 is the boundary. Okay, nx minus 1. Similarly j is equal to 2 to ny minus 1. Okay, so first I'll calculate txx. Okay, so I'll be using the central space, so I'll be using second order scheme. Okay, so t old of, this is j comma I plus 1. minus 2 star. You should be very careful while writing these indices, okay? Now similarly you can write TYY also. Okay, so J index is the Y direction, so J minus 1, J plus 1. Okay, and then, okay, this is not just enough, you have to also write divided by del x square square. Okay, so now you can write T old, sorry, T new of j comma I is equal to T old j comma I, that is the Tn plus 1 is equal to Tn plus alpha is there here. Okay, just I'll copy paste this. Okay, what is this? Txx plus Tyy. Okay, so this is done. So we have set up this. Okay, we have calculated. So now we have to calculate either global error or local error. I usually go with a local error, and it is quite easy to calculate that also. Okay, local error. So I want max error is equal to, so individual we will calculate first and then take the maximum of maximum. Okay, so that is the T old minus T new, and make sure that you have to take the absolute value also, because sometimes it might be negative. Okay, T new minus T old. Okay, so but if you just do this, it will take the boundaries also into account. So what I usually suggest is you take the values apart from boundaries. So usually 2 to ny minus 1 and 2 to nx minus 1. Okay. So I am leaving out the boundaries. Okay. Boundaries I am not calculating the error. If you just do t new minus t old, it will take all the values in the array. So I don't want to do that. I don't want to calculate the error on the boundaries. The boundaries we already know. Okay. So that is why only these many terms I am taking. Okay. So this is how I calculate the max error. So I will check whether it is going beyond 10 raised to minus 4, then continue. If it is going less than 10 raised to 4, this while loop will get exited. Okay, so it will leave the while loop and it will come out. So when it comes out, I just want to plot the contours of, say, x comma y comma t old. Okay, and then maybe you can take the color bar also. Okay, and you need to define x, what is x and what is y. Okay, first of all, so you can do that using the linspace. It divides the space into equal number of, say, 0 to lx comma nx. Okay, ny, ly and y. Okay, now maybe you can run the code and check whether everything is going correct or not. Okay, usually you get some errors, you have to try to debug them and see what is going wrong, but I hope there should not be much issues here. And if you are specifying some unrealistic boundary condition, then this might not come out at any instant of time. Okay, so it will go into infinite loop, so that may also happen sometimes. And usually you need to keep a monitor. Okay, say you can try to keep a monitor like display max error at each and every time step. Okay, so that also you can do to check whether it is going, whether the solution is diverging or what. Okay, so I have displayed the maximum error at each and every time step. Okay, here. So yeah, it is keeping constant. So these things might happen because one thing, it might be because of your unrealistic boundary conditions, or you are doing somewhere some mistake in your code. So it might be because of both the reasons. Okay. So the main thing is we have not included delta t. Okay. Although I told that utt is equal to, sorry, it's not utt, it's just ut. Ut is equal to this thing alpha, so you have to include also del t. Okay, that is also important. So again it is coming constant. So can you guys tell what might be the error in this particular code? If any of you can say. Okay, it might be because of boundary conditions also. Okay, so that is one thing which might be the case, or else there might be something else also which we are missing. So we have usually t new minus t old, say, divided by delta t is equal to alpha into this thing. Okay, so that is there. I think that is getting calculated properly. The main thing, there might be some issues with this txx or tyy. So why is error max is absolute of absolute? It's not absolute of absolute. It's just why we have to take absolute is this t new minus t old. Sometimes what it might happen is it might go into negative value, but we want to take only the absolute value. And why max of max? Because usually what happens is that when we have a 2D array in MATLAB, what happens is that when we take max, it gives 1D array of maximum values along the columns. So then we have to again take a maximum so as to get one single value. Okay. So but what is happening in our case is that it might be because of some issues with the boundary condition also, that we are getting a maximum error which is constant at one particular grid point, and that is staying the same for all the time steps. So that is why we are getting 15, 15, 15 at all the time step values. Okay, so I have taken a boundary condition from one of your assignment problems actually in the other code. Okay, so which I had written just previously. Okay, so in this actually it was kind of working quite well. So these boundary conditions I had taken from the assignment. So in this, the other things remain same here. Okay. Okay, so one thing which I missed, I think. Okay, updation. So always we have to do the updation after each time step gets over. Okay, t old is equal to t new. Otherwise what will happen is that you are calculating t new. Okay, the t old is remaining the same. Okay, which is there at the initial condition. Okay, so that is one mistake which we have done. So you have to update the t old with the t new as the time progresses. Okay, So here you can see that the errors are kind of reducing, which you can see from this. Okay. So now it has stopped because it reached 10 raised to minus 5. And then you should get the contour of the temperatures. Okay. So this is the contour. So you can see that at the west boundary and at the north boundary, you are kind of getting constant temperature values which we have specified, and at the east also you are getting 200 which we have specified. At the south boundary we had specified an insulated boundary condition, which means that dt by dy was 0. Okay, that is why you can see that you get a vertical line near the south boundary, okay, in the contour. So this is the main reason. So this is how your contour of temperature will look. Okay. So are there any queries with respect to this particular code which we have written? Okay. So you also try to write some code in whichever programming environment you are familiar with. Okay. So this will definitely build a confidence among you to go further. Okay. Just don't start with Navier-Stokes equation or something like that. Okay. I have used contour. Okay, contour F. It gives a filled contour. Okay, you can check about this. Okay, online. Okay, regarding MATLAB. Okay. Okay, so let us try to see some couple of questions. Okay, so anyway, the questions and answers which I have solved, I will be uploading them. Okay, on the Google Drive, you can also see them later on. Okay, so the first question, sorry, the first question is, which of the following equation models propagation of sound waves, that is the acoustic speed in air? So can you write down the answer? We have discussed about this during the starting of the session only. Okay, sound waves are modeled by which of the equations? Yeah, it should be A and B both. Okay, because as I told, there are two things. Okay, one is the sorry, one is this acoustic pressure as well as acoustic velocity also, which are modeled by these two equations. If they had specifically asked about pressure, then I would say that only one would be correct, that is the second order equation. But anyway, that is not discussed in detail in the weekly content also, so both the options are correct. Okay, both A and B. Okay, so now let us try to go to a next question. Okay, in this particular question, it is asked, what is the finite difference approximation of first order linear wave equation, okay, using again forward times central space, which we just saw in our code now, if the spatial discretization is performed using fourth order central. So instead of second order central difference, fourth order central difference scheme is used. Okay, so we have to try to derive the this indicial notation for the first order linear wave equation. So the equation will be as follows. So it is our dou u by dou t plus a into dou u by dou x. That is the equation. Okay. So for this, you need to do two things here. So for one thing is, for dou u by dou t, you need to write down the indicial notation, that is the discretization. Then for dou u by dou x, using the fourth order central difference scheme. Okay, so if the chart is given to you in your examination, then it is well and good, you can just go through it and calculate the discretization. Otherwise you can use the Taylor series approach also to calculate this dou u by dou x using the CD4 scheme. Okay, so first, the dou u by dou t can be discretized using the forward time as ui at n plus 1 minus ui at n divided by delta t. So that is one thing. The second thing is dou u by dou x using your fourth order central difference scheme. It can be described as follows. So this you can try to see using the chart also, or I mean using the Taylor series also. So this again, it will become u at I minus 2 minus 8 into u at I minus 1 plus 8 into u at I plus 1 minus again u into I minus 2 u at I plus 2, sorry. So this is usually symmetric in nature, that you have to remember. For the upstream direction and for downstream directions, the numerical coefficients are symmetric in nature, only the sign reverses. So that is the thing which you have to keep in mind. So once you have kind of come up with this, okay, then you can directly substitute this, okay, dou u by dou t and dou u by dou x, the indicial forms in the equation, okay, and then try to get the solution. So uh, seeing this equation, what should be the correct choice for this question? Can you write down in the chat box? Okay, it should be, it should not be C, it should be D, because remember for I minus 2 we are getting a negative sign, okay. Why we are getting a negative sign is because here we have a positive sign on our LHS, okay. When it goes into the RHS side, it becomes negative, okay. So although I am getting u at I minus 2 is it's coming out to be positive, but since it goes into RHS, it becomes negative, okay. So that is why uh, the option number D should be the correct answer, okay. So let us come to the next question. So in this, what is being asked is, so you have to determine the value of current number and the amplification factor for the same question, that is question number 2, the previous question, and all the other things are given. So can you guys write down what should be the value of current number first on the in the chat box? You have studied that current number is used to mainly gauge the stability. So in some range of current number values, you get a stable solution. So what should be the current number for given values of delta t and a? Yeah, it is a into dt by dx, correct. But what should be the value? Because these values are also given, a value, delta t value, and all. Okay, it should be, yes, 0.06. Okay, so that is one thing. Okay, the second thing is we have to calculate the amplification factor. So amplification factor is given by the ratio of the variable at n plus 1 at and n. Okay, so you have to determine the indicial form first, so that we have done in already in question number 2. Okay, so that I have written here. Okay, so this is the indicial notation, okay, so which we have already calculated in question number 2. So here you have to just substitute this form here, okay. Ui at n plus 1 will then be equal to capital U at n plus 1 into this e raised to I theta I, whatever is there, okay. So that you have to substitute here, okay. You get this particular equation, and when you kind of divide this particular equation, okay, by say un into e raised to I theta. So this is general procedure which you do, okay. I'll not get into much details, okay. You get a particular equation, okay. So if you are substituting a delta t by delta x, which is 0.06, which you have already calculated, okay, and then expand these things, okay, whatever e raised to minus 2 I theta using the cos plus sign, you kind of finally get into g is equal to 1 plus 0.08, okay. Now this is anyway you can calculate it independently, okay. What I want you to tell me here is whether this solution will be stable or not. Can you write down on the chat box? I don't want the answer, final answer, whether it will be stable or not. Unstable. Please explain the same case with A is less than 0. See, in A is less than 0 also it will be the same thing, but G value here you will get in an opposite way. Okay, so let me tell you. So what happens is this current number we usually write it as magnitude of A into delta T by delta X. So since A is less than 0, what happens here is that there is a minus sign which comes in. Okay, instead of plus you get a minus here. Okay, minus you can write C. Okay, C by 12. Okay, so everything will remain same. 1 minus C by 12. Okay, so here also what will happen is 1 minus 0.06 divided by 12. Okay, I hope you can understand that. Okay, so what will finally happen is 1 minus 0.08 I you will get instead of plus 0.08 I, so you will get a minus 0.08 I. Okay, so that is what usually it happens. Okay, uh, so in that particular case also, and in this particular case also, whether it is A is greater than 0 or whether it is A is less than 0, the scheme will become unstable because magnitude of G will become greater than 1 because it will be root of 1 square plus zero point 0.08 square. Okay, so Dibyendu, I hope I have answered your query. Okay, so everything will remain same, only it will become 1 minus 0.08 I. It will basically start from this point. Okay, here it will become minus of magnitude of A delta T by delta X. Even if you don't take magnitude, you should directly put, say for example, minus 1200. So you directly put minus 1200 here. Okay, so that is how you do it. Okay, everything else will remain the same. Okay, I hope that answers your query. Okay, so yeah, so for this question then the solution is unstable. Okay, and yeah, either it is greater than 0 or less than 0, it will be unstable only. Okay, okay, so the option should be B. Okay, so I think the question number 4 was also something related to that only, I think, which the Priyantu was discussing. Okay, so the forward time, forward space, what should be the I think amplification factor, that was mainly asked. Okay, so you have to go in a similar manner. You have to first come up with an indicial approach. Okay, so what I have done is here current number C I have taken it to be magnitude of A delta X T by delta X. Since A is having a negative sign, so what happens is that this becomes plus. Okay, here it is the reverse. Okay, because it comes into RHS and you by default you have minus, but since A is less than 0, you make it plus. Okay, current plus C. Okay, so that is the change which happens. Okay, so in this way again you can calculate the amplification factor for this question also. Okay, so anyway these will be attached in the Google Drive and the link will be shared. Okay, so are there any queries with respect to the coding problem which we solved and these particular questions? If there are any queries you can ask on the chat box. I'll just share the YouTube link. Okay, just hold on for a second. Google Drive wherein these things will be shared. That link I'll share first. Just stop sharing the screen. Okay, and then the YouTube channel where these videos will be uploaded. That link also. Okay. Okay. Yeah, there was a question, I think. In case of TDMA, okay, let me do one thing. I'll just, yeah, Dibyendu, can you unmute and ask your question? because I did not get your question correctly, I think. In case of TDMA with Dirichlet boundary condition, what is your question? I think you can unmute and speak. Or else if it is not possible, then you can maybe write on the chat box only. In case of TDMA with Dirichlet boundary condition, for n nodes we get, no, for n, if you have say n grid points, okay, so you come up with n minus 2 equations, right? Why do you get n minus 1? Minus 1 equation is sufficient. No, n minus 2 itself is sufficient, not n minus 1. If you have all Dirichlet boundary conditions, and if you have n grid points, I mean, if it is in 1D, I am talking about 1D, okay. Last Dirichlet boundary used in last substitution. See, first also you use it, right? Like the, let's say for example, if you have left and right boundaries which are Dirichlet boundary conditions, okay. So for example, if you are coming up with a linear algebraic equation for a second grid point, then you use the Dirichlet boundary condition of the first grid point, right? So there also you get one equation less, and similarly on the right side also you get one equation less, right? So only n minus 2 equations I think you'll get. Because those things will go on to the b value when you get ax is equal to b kind of system. So those things will go on to the b side, okay. So you will have only n minus 2. The matrix will be n minus 2 cross n minus 2, okay. Yeah, okay, okay, yeah. I hope you have understood that. Okay. Okay, if it is Neumann boundary condition. Now what happens in Neumann boundary condition is, say when you kind of derive the uh, equation for the second grid point, okay, so you have t of 1 also. So for example, if you are doing it for t of 2 equation, but you know that t of 1 is equal to t of 2, okay. So in the equation itself, you have to substitute t of 1 is equal to t of 2, okay. So then also it will be n minus 2 only, okay. Yeah, it's the same procedure, okay. If you are not understanding, just let me just share my screen and just explain that, okay. See, for example, if this is 1 and this is 0, t of 0 is equal to t of 1 if you have it, okay. Then for the first grid point you have one equation, okay. T of 1, here you will have t of 2 also, here you will have t of 0 also, but t of 0 you know it is equal to t of 1, so it will become 2 into t of 1. On the b side it will be 0 only, okay. Again it will be n minus 2 only, okay. Yeah, n minus 1 or n minus 2. Similarly for the last grid point also you can do the same procedure, okay. Or else, yeah, as you are telling, you can do that procedure also. This is what usually I follow, okay. What you are telling is you can do like t of 0 minus t of 1 is equal to 0. This also you can take it as an equation, okay. This also you can take it as one particular equation, okay. So then you will have n cross n matrix only. if you are doing it this way, but there are two ways. Okay. So, for example, if you have Neumann boundary condition at both the ends, so you get t of 0 minus t of 1 is equal to 0. You get similarly t of n minus 2 minus t of n minus 1 is equal to 0. Okay. So this also, if you take it as one particular equation, you can take it like that also. Okay. So there also, in that way, if you do, you will get n cross n. What usually I follow is that in the second grid point equation, substitute here only t0 is equal to t1. Okay, then it will become 2t2. So I'll just avoid that two equations. Okay, so I hope that is clear. Can you share the Google Drive link again? Just a second. Yeah, if the flux is not zero, what you usually get is on the B side you get some values. Okay, but again you can reduce it. Okay, but if it is becoming difficult, then you can just do with the taking it as separate equation, the first method which I told. Okay, I've shared the Google Drive link. Okay, but in any condition, what I feel is that you can reduce it. You can reduce it and make it n minus 2 cross n minus 2. Okay, but you can also go with n cross n. Okay, so that also is possible. If, say, for example, there are too many terms. Okay, and if it is becoming difficult to reduce, you can go with that also, but you have to check whether you will be able to apply TDMA or not. Okay, so that is one thing which you have to check. Okay. Okay, so I hope the things are clear now. If any of you have queries, you can ask, otherwise you can leave the meeting. Okay, you can see the other questions on this Google Drive link which I have shared. Okay, there the PPT will be available, so I have shared. No, I have not shared it till now. After this class, I will share. Okay, you can maybe check it after some 10 minutes. Okay. Okay, thank you for attending the class. Okay. So, bye.